I will talk about building a distributed robot garden, and as Dale already mentioned, the HEMBI perspective is pretty clear here. There are so many authors on the paper, so all of them had to interact with these robots and that plant system. So our vision is actually to get autonomous precision agriculture. And precision agriculture is something which has already been done as a word that people use. It's when you apply water and fertilizer very precisely. But what we want to do is we actually want to build robots that can manipulate individual plants. So right now you have these big combiners, these big machines to harvest all sorts of fruits. But what I really want are little robots that you can send into a greenhouse with all sorts of different plants. And then the robots make like little piles of fruits around the greenhouse, and you put in water and energy. And so if you can do this, then you can have diverse versus monocultures. So you can have different kinds of plants that maybe even interact with each other, help each other out with pesticides and pest repellents and fertilizing each other. The other thing is, if you can do this, you might build buildings in big cities where you integrate agriculture into the building. So people could, like in this data center, we have now that garden, and a lot of people just walk through that and see that garden and wonder what people are doing. But they also enjoy probably the sight of some plants and some nice light that lights up there. And also, you might be able to put systems into deserts where water is really precious, or even into space where you can cultivate crops for astronauts. So my other vision there is that we really want to do plant-centered sensing and control. So each plant should know about itself and should have some sensors that it can communicate to the robot, and so basically having a computational interface. So as I said, I think if you do that, if you really measure on the plant what the plant needs, you can really preserve water and you can really preserve fertilizer. And so people have been working in that field, especially automation is something that is very widespread. So people have been harvesting apples and cherries and tomatoes and mushrooms. So this shows one of the robots that does tomatoes. It's in Japan. It's a huge robot and drives in this field. There are also people working in sensor networks. So people have been putting humidity sensors and light sensors into big fields or greenhouses like you see below. And finally, there are also people working with intelligent environments. So you have a kitchen, for instance, where you have sensors in the appliances and you have robots interacting with them. And I think what we do is actually an intersection of these three things. It is some harvesting technology plus distributed sensor network and taking advantage of intelligence embedded into the environment. And so what we did is we have this little greenhouse, I call it. It's just over the road. And we have 4 tomato plants that we want the robots to water and to eventually harvest. And so what we do is we have a little computer with every plant that monitors the humidity level and also coordinates the robot. So the plant actually tells the robots, please come water me, please inventory me, or please pick a fruit of me. And so this inventory step is something where the robot can go and use its vision sensor and its arm and sweep the tomato plant and tell the pot. So you have so many fruits, they are located here and there. Some of them are green, some of them are red. And so the tomato plant knows at all time how many fruits it has. And when the user sends a harvesting request, the tomato plant can actually say, I have some nice red fruits, and can tell the robot where it has to grasp it. So that was a student project. I will come back to the educational perspective of the project at the end. And so what we did is we had actually 2 years time in that project, and we had 2 summers and 1 class and 1 independent activity period where we had different cohorts of students that came into the project, and each time we tried to create a self-contained project for them so that they can finish something. And then we took that and went from there for the next group. And so what you see today is essentially the 3rd or the 4th iteration of the system. So the robotic platform we have, and now it will get very technical, not very technical, but just I want to show you, I'll give you an appreciation of what how many things robotics brings together. And so the robot we built has an arm to manipulate, has a camera to see, it has a drive train, which is just an iRobot Create, which is like a Roomba vacuum cleaner, but for research. It has a watering system, so it has a water bottle and it has a pump running up a little hose to the, I wanted to say mouth or beak, but it's actually just an arm. And we put a notebook computer on that, which does all the computation and wires everything up with USB. Finally, we also have a localization system, which can work like a GPS system, but indoors. So now the plant, we have every plant, so we talk about intelligent pods, because every pod has an infrared beacon, so it can attract actually the robot and help the robot to home right into the pod. It has a wireless router, which has a temperature sensor and a humidity sensor in the soil. And the humidity sensor is some product from Arizona. There's a company that makes just these sensors for greenhouses that we put in the soil. So the principle of operation of the whole system is the plant monitors its own status. It monitors the humidity and the fruit location. And then when it needs something, it tells the robots, I need this, I need watering, I need harvesting, or I need inventory. And the plant actually assigns that task to the closest robot. So the plant will say who is close by, who's idle, who can help me out, and the best robot that is closest by will actually then get the job. So now the system architecture of the system got pretty complex pretty soon. So this picture I actually took from the DARPA car that MIT built. I just wanted to get an idea how other people display such a complex system. And I was actually surprised that I had to fill in all the little boxes that they had, because you have a lot of sensing going on. You have a camera, you have an odometer, like in a car, you know how much the robot has driven. You have a bumper sensor, you have an infrared sensor, you have a force sensor in the arm, and you have a humidity sensor. And now you have to develop algorithms that take this sensor measurements and create some meaningful information that we can process. So we have all these perception algorithms that then get taken into a planning and control part where we have logic which describes how the robot is acting and how the robot is controlling its arm using the camera, for instance, the visual servoing module, or how to move the arm so it doesn't collide with anything, which is the arm planner module. And then it takes all these calculated information and sends it to the actuators, which are the watering system, the arm, and the drive. And just for anybody interested in robotics, there's an open source robotic system that we adopted, ROS. So the whole thing is open source, and you can download it actually and play with it. So the first module that I wanted to talk briefly about is the navigation. So it's actually a hard task for the robot to move on a map or to move from plant to plant. And it turns out that you actually need some sort of GPS. You need to know your absolute location in the environment, because otherwise you get lost and that's it. The robot cannot recover from that. So what we did is we took odometry and we fused it with that GPS sensor, and then we used a planning algorithm to plan an optimal trajectory on the map that doesn't collide with the obstacles or any other robots. So all robots have wireless communication and then can tell, I'm here, please don't run in me, and then they plan a path around each other. The next module is task allocation. So I told you the plant actually issues the chores that the robots are supposed to do. And then the robots say, I'm so far away from you, and I have so many minutes worth of tasks already in my queue. So then let the plant decide which is the robot which is actually the closest and has the least tasks to do to select the job. And so I want to just tell you why do I have these little planners, these modules here for you. These are all distinct research areas in robotics. So there are people that just work in navigation, there are people that work just in task allocation. And we didn't want to reinvent the wheel. We pick up what we could find, but our contribution really is putting that all together in a working system. And this was by far not, I would have loved to say it was so complicated as Dejan's work, but this is actually he has another order of magnitude where you really have to build stuff that has to work. So we didn't have all these problems. But already when you build something simple as that in comparison, it will just not work because there are too many things that can fail. If you have like 20 modules like that, and that was a tremendous experience for the students to put something together that they know from a textbook and that they think, oh, it's just easy. I just take that module, put it together with that one. And they have to go to that nice days and night and put that together. So to give you an idea about the results from the navigation, with odometry, when you drive just 1 meter in a square, you have already an error of like 10%. So we then had to add this GPS location sensor, and now we could drive 20 plus rounds around the little garden environment that we had. And also we could do the watering in 100 plus trials, and it always works. The other, and that's probably the hardest part of the project, was the perception algorithms. So the thing is, you want to detect where are these tomatoes. And we were very ambitious about that in the beginning, and we tried a feature-based approach where the students hand-tagged images of tomatoes, and then the computer tried to learn what are relevant features of tomatoes. And then what it does, it takes these 40 features that it learns, and it makes a convolution with the image that you see. And then when the convolution is high, this is where tomatoes are likely to be. And so as you can see, it's pretty unclear where the tomatoes are, and it works in this example, but I will show you in the next slide. It is actually very computationally expensive, and it has a pretty low success rate. The other approach we did is just a filter base, and I say just because that's what you would classically do. You just filter the image for colors, you filter it for smooth areas, so there are some mathematical operations that give you areas in the image where it's smooth. You look for spectral highlights, every tomato has these, or you look for circles in the image, which is another filter, the U-transform. And so we did both of these things. So first we did the complicated one, and then we realized why not trying something easy. And so it turns out that when you do the feature-based approach, you have only 34% correct estimates of tomatoes. And with the filter base, we could do it to 75% correct predictions. And this also gives you already an idea how the system works. It's essentially probabilistic. So the robots don't really get a 100% idea of how the real world looks, but they just get some estimate of what they can see, and that's how they have to plan their actions. And so we tried to overcome this by also using a probabilistic approach to managing the data. And so when we do the inventory, this is something where the robot actually moves the camera to distinct locations on the plant. And whenever we think we see a tomato, we mark that location with 75% likelihood. And then when you go over that again and you find a tomato at the same place, you can actually take these two probabilities and you get something like 95%. And so every time you see the tomato again with your 75% estimator, you increase the likelihood of it being there. And if it doesn't show up anymore, you discount it. And so then the arm can always grasp the tomatoes which are the most likely to see. So the next module is visual servoing, and here the task is, or the problem is, if you have 4 degrees of freedom or you have an arm, how do you have to move actually your joints so that you move the camera, the arm right to the object? So you see, this is my goal, I have to grasp that tomato, and so how do I calculate the arm movements? And this is a pretty established science. There are algorithms for doing that, and we tried to, or we actually did grasp the tomatoes. And so when you don't see the tomatoes, or we have only 34% likelihood, then most of the time it fails. And so we could then, using the filter-based approach, bring that up to 75% correct grasp. So 75 out of 100 tomatoes that the robot sees, it can actually grasp. And so you see also there's a correlation between the likelihood that you have to the reliability that you have on your sensor and the reliability of the overall system is pretty well reflected in that. So that's actually a trajectory of the error that you see. So you have your arm that has to move to the tomato, so you have that error between that. And so you try to minimize that error, and you move the arm along that, and you see how the error finally converges. And that's actually when you close the gripper and take the tomato. So this is a video. so it just said that it got a watering request, and now that's a typical thing in robotics. You have this multiplicator to run stuff faster because it's so horribly slow always. And so now they try to dock to these tomatoes. And so he starts now watering. And I think the other guy is also watering. That's probably their task. So that's the highlight of the video. And so he says, I got an inventory request. And now what you're going to see is this motion that I described to you. It will go to the tomato plant here and wave his arm with a camera to scan the whole plant. So this are these distinct points, and so you see what the robot is actually seeing, and it doesn't find any tomatoes there. And so that's the last motion, and there are some tomatoes actually even. So that selection step is it selected the tomato with the highest likelihood of being available, and now it grasps it. And so this was actually a huge problem because we run out of tomatoes. It turns out that if you don't change the soil, it gets pretty acid because of the minerals in the water here. And we changed the plants once, but it's just whenever the cameras came, then there were no tomatoes. Or the plants had pesticides or some, pests. And so what I want to do now, I think we should even take more advantage of the distributed computation capabilities. So if the plant knows its fruit locations, why not using a computational model of growth to measure, let's say 2 weeks ago, it had all the green fruits. So you know, it's a very simple model actually. After 75 days, the plant cycles, so it's very likely that it will have red tomatoes in 2 weeks. And so if you use that system to actually calibrate the plant model, you can get better every time and eventually don't rely less on sensing. The other thing is we were hoping to actually grasp every tomato with this cheap system that we had. And I say cheap because it's off-the-shelf hobby consumer robotic stuff. It's not the $100,000 robots that people usually would use. And we actually found out that the tomatoes are so weird. They have these I don't know the word actually for that, but the stem coming out of it in like 50 degrees or 90 degrees. So you actually need much more degrees of freedom than we thought you would need to actually grasp the tomato. And the other thing is you just not want only know where the tomatoes are, but you need the whole topology of the plant because you have to plan between the branches. And that's something that happened a lot where the robot just run into a branch that it couldn't see, or because it is extensions of it touched that. So we want more sensors and maybe get a whole 3D reproduction of the plant. And if you divide computation and sensing and actually doing the harvesting task, as we do, by storing it on the plant, you can actually afford to have a robot that takes 1 hour or 2 hours to scan the entire plant and it just goes to the next plant. After 2 weeks, you have all your plants scanned. But then when the robot comes in, can immediately use that information to a certain extent to actually do the task. So that's the heterogeneous system bullet, where you have like one expensive robot that actually does all the heavy lifting on the sensing, and then you have the cheap workers. So educational, what I really liked there was we chose the project because it exposes students to a real-world problem. So real-world, I don't mean economically viable, but I mean something that is not a block world. So it's not a white arena with like pink balls like the Sony Aibo has, but it's something that's real, and that challenge comes with real challenges. The other thing which I try to bring you nearer is that it's really comprehensive robotics experience. You have almost all the disciplines that are in robotics together and get exposed. And the nice thing was we had actually, all the students were exceptional, but we had also some that have some previous experience, and they brought in their experience and solved problems in ways we didn't know about. That was one thing, and the other thing was they also taught each other about what they were doing. So everybody was focusing on a specific project in groups of 2, and what then happens, in order to put the system together, they have to actually talk to each other, they have to explain each other how the visual serving works, how does the navigation work, and at the end they know much more than you have taught them, and probably in a more deep way than we could ever reach out to them. So the other thing is the plants were actually something everybody learned a lot. So we had this great student who is a hobby gardener, and he came with this plant growing hormone, and he put that around the stem, and it actually was supposed to grow roots out of the stem at that point, so that we could take off that plant and put it into the earth somewhere else. And it didn't work actually, but we all learned a lot about gardening, and we had to actually solve these problems. We had to find out, what do we do with these pests? We had tremendous pest infections all over any time we ripped them off and put new ones in. 2 weeks later, we had all these pests again, we had diseases. So we had to think about how to solve that, and that was a nice experience, I think, for the students who often are very focused on engineering. So I mentioned the unexpected things. So the conclusion is we demonstrated the watering, the inventory, and the harvesting on a conceptual level. And I think one of the technical contributions is really this idea of distributing computation and sensing in the environment, taking advantage of that, and then use cheap robots to do stuff which they couldn't otherwise do or would do much slower. We had problems with that limitation of the platform because 4 degrees of freedom are just not enough to reach out. And also the workspace was not big enough, so you really need a big arm that can reach everywhere on the tomato, not like in a small sphere. And so what we're currently working on is to have a more persistent installation where the robots are really running for weeks unattended and do the watering. And I want to do the same thing at Boulder in an undergrad housing where there's interest to do some robotic stuff. So I think that's it. We have a lot of sponsors for this, and I was especially glad about the Europe office of MIT and the summer research project, which brings in great students from all over the country, which were tremendously helpful and actually did most of the heavy lifting of the project. Thank you.